Hey guys, I'm not sure if this is going to be a part 3, if this is still part of part 3, or if I accidentally made a part 4. I went to pause my video to answer the phone, and I think I started my recording over. So, yeah. Okay, so we were, I don't know how it's going to work, but this was, so we were on a depreciation problem. And so when you buy a brand new car, the second you drive it off the lot, it's considered pre-owned. And so if you decide 5 minutes after buying it that, you know, this was not a good idea, I don't want to do it, and you go to return it, it's not worth what you paid for it. It's worth less. So yeah, so you gotta be real careful with buying cars. Like, cars don't hold their value. If you think about a car you would have bought 5 years ago is nowhere near as nice a car you'd buy today. So, okay, so we've got, Chris has got a car, and as a general rule, a car loses about 10% of its value each year. I think nowadays it loses more, but, you know, just as a general rule, about 10%. So Chris bought this new car for $27,000. And it loses 10% each year, which means that if you lose 10%, it's now worth 90% of what you paid for it. So if you lose 10%, it's worth 90%. You're subtracting that 10% out of the 100% it was worth. So that's where this 0.9 comes from. So they give us the equation. They give us V of t equals 27,000 times 0.9 to the t value, or to the tth power. So looking at it, like, if you didn't know what to do, if you read this problem and were like, I don't know, I have no idea what to do, all you have to do is see the fact that we have t years and we want to know how much it is for 10 years. So t stands for years, and we want to know something about 10 years. 10, you replace the t with 10. Okay, if you didn't know anything else about this problem, you could figure this part out. If you didn't know anything about exponential functions, you could figure out that, hey, look, I should take that t and put the 10 in for it. That's just a good test-taking strategy. Now, reading the problem, we see that, well, I mean, just what I said. Reading the problem, we see that we have our initial value of 27,000. We have our depreciation value, and we have our exponent for years. And if we want to know the value after 10 years, we're going to put 10 in for t. All right, so let's get some math on this. You just plug this straight into the calculator. 27,000 times 0.9 to the 10th value. You're going to get that V of t is equal to $9,414.32. That's all you have to do. This is a calculator problem. That's it. Plug it in, get an answer. Just plug in simplify. Okay, 18. One of my favorite questions. It's not really a math question. Is, do you remember something I told you about exponential functions? Okay, so I want you to come up with your own equation that represents exponential growth. Okay? So let's have some fun with this. Alexa, pick any random number.
84 is a random number.
Okay, let's use 84 as our initial value. So we have our initial value can be anything. It can be a whole number. It can be negative. It can be, I forgot where I was going with that. It can be a whole number. It can be negative. It can be a fraction. Doesn't matter. Then let's go with our growth factor. Alexa, what's a random number?
Avogadro constant is a random number.
Okay, not that one. Alexa, give me a random whole number.
Minus 571,734 is a random integer.
That wasn't what I asked for. I asked for a whole number. Alexa, pick a random number between 1 and 10.
Your random number between 1 and 10 is 4.
Okay. 84 times 4 to the t power. So this is an exponential growth function. Now I didn't put a lot of effort into picking my numbers. Obviously I picked random numbers till Alexa started decide. You know, the last time I asked her, she was like, here's 2, 6. And then this time she was like, Avogadro's constant. Are you kidding me, Alexa? Goodness. Okay, so plugging in.
Hope you had a great day.
She heard me. So, okay, so the reason I know that this is exponential growth, remember, exponential growth means that when you graph this, you're going to increase from left to right. Which means if I'm multiplying by a constant, it needs to be a constant that's going to make my number grow larger. Which means my b value, or my common ratio, needs to be greater than 1. So if you remember, our exponential function, like our pattern for it, is a times b to the x, where a is an initial value and b is our common ratio. So our common ratio for an exponential growth function needs to be greater than 1. Okay, so let's look at decay. If growth needs to be greater than 1, then decay, which is the opposite, where I'm decreasing from left to right, decay needs to be less than 1. But I can't just say a number less than 1, because then we could have negatives. And negatives doesn't necessarily mean it's decay. In fact, a negative, you could have -2. It would grow negatively exponentially, which is weird. It's not really decaying, but it's not really growing. It's in this weird, I don't know. We don't deal with negatives right now. We're not. When our growth factor is less than 1 but more than 0, it's a decay factor, not a growth factor. So when our common ratio is between 0 and 1, it's decay. So Alexa, pick a random number between 0 and 100.
Your random number between 0 and 100 is 8.
Oh my goodness. Your random number is 8. Oh my goodness. She couldn't do that when I needed it. You know what? Let's make it big. Let's do 8,123. Just for fun. Okay. Alexa, what's a random number between 0 and 1?
Here's a number between 0 and 1. It's 1.
No, that's not what... Alexa, what's a random fraction between 0 and 1?
1's fraction representation is 1, 1.
Okay, never
Does
mind.
that answer your question?
No.
Thanks for your feedback.
Okay. Random, let's do 3/4. To the t power. Okay, Alexa was not very helpful. Oh, she heard me again. Darn it. Okay. So anyway, here's a decay function. My b value is less than 1, but is greater than 0. So my common ratio is between 0 and 1. I hope this video has been fun for you as I struggle with my smart device that's in my classroom. I'm not saying her name so she doesn't hear me. Okay, so also it did say, how do I know it represents exponential growth and exponential decay? Because you could have linear growth and linear decay. How do you know this is exponential and not linear? Easiest answer, it has a common ratio instead of a common difference. The even easier answer is that it has an exponent and or an exponent of x. So, or your input is an exponent. So it's exponential growth, not linear growth. But I mean, the more mathematical answer is that there's a common ratio rather than a common difference. That's why it's exponential. All right, 19. Man, I've only answered 2 questions, and this is probably going to be the longest video because I'm arguing with a little disc in my room while filming. All right, 19. Match the function with the graph and then explain. Okay, So when I go to look at this, I've got two graphs. They're both exponential. So looking at, trying to figure out if it's exponential or absolute value or quadratic or linear, that's not going to help me. What's going to help me is kind of A, determining whether it's growth or decay, and B, looking at where my boundary line is and looking at where it's shifted. Okay, so the first thing I want to look at is whether or not it's growth or decay. That's going to be my biggest tell. So remember, a function, if the common ratio is less than 1 but greater than 0, it's decay. So this right here tells me that I'm looking at a decay function. My common ratio here is 2, which is greater than 1, so that tells me I'm looking at a growth function. The next thing I want to look at is where it's shifted. So remember, if you look at this minus 2 at the end, that's going to tell me that my graph has shifted down 2 units. This plus 2 will tell me it's shifted up 2 units. Hopefully y'all remember that from first semester, that subtracting shifts your graph down, adding shifts your graph up. And then you also have this minus 1 that's right by the x. So this is a horizontal shift if you're subtracting or adding from the x. If you're subtracting 1 from x, it should shift to the right 1. And I know a lot of people are like, well, wait, negative is to the left. Remember, it's opposite on horizontal shift. It's opposite from what you would expect. So this would also shift left, but 2 units instead of 1 unit. I'm sorry, shift right, not left. Okay, so let's look at, we need something that has, that's a decay function that has also shifted down. So if you remember, decay function should decrease, and normally this boundary line, remember, it gets infinitely closer to 0 but doesn't touch. But if it's shifted down, this should be getting infinitely closer to negative 2. So if I look, equation number 1 is a decay function. It's decreasing. And my boundary line, if you see this, this is getting infinitely closer to negative 2. It's shifted down 2. It's getting closer to negative 2, not closer to 0. So this matches with function A. All right, number 2, this is a growth function. As you go from left to right, it increases. And then if I look, this is getting infinitely closer to positive 2 instead of 0. So it's been shifted up 2 units. So this matches with function B. All right, number 20 asks us to identify the domain and range of these graphs. So A, my domain. Now remember, in the examples we did in class, they were all real-world scenarios, right? So our domain always was greater than or equal to 0 because our domain always measured time, and we don't have negative time. However, these aren't real-world scenarios. These are just graphs. These are just pictures. We're just looking at all the possible values of x. So if I look at A, if I were to zoom out, I should still touch every single value to the right, and this function should touch every single value to the left. There's not an x value that can't be put in this function. If I look at this equation, there's not an x value that I cannot plug in. If every x value I plug in should give me a y value. If there was one that I plugged in and didn't get a value for some reason, that would be excluded from my domain. But every single x value I plug in should give me a y value. So my domain is all values of x such that x is all real numbers. I can't remember how to read it correctly, but my x is all real numbers. Basically, there's not a number that I'm not going to have a value for. Now my range measures my y values. So if I look at my picture again, as it goes up, there's not a value it's not going to touch. It's going to touch every single y value going up. But coming down, it levels off, and remember, it's getting infinitely closer to negative 2, but it never actually touches negative 2. So my y values are every single y that is greater than -2, because remember, it doesn't touch -2, it doesn't go past -2. So my y values are greater than -2. Okay? Oh, you can't see that. So my domain is all real values, or all real numbers. My range is that y is greater than -2, because it's, again, this is getting infinitely closer to -2, but it never actually touches. For B, my domain is it's going to be exactly the same. As I go from left to right, I'm going to touch every value on the left. I'm going to touch every value on the right. There is no value that I cannot plug in. So my x values are all real numbers. Okay? Now my y values. So as I look at this is going to go up, 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 up. It's going to touch every single value that's greater than what I'm thinking of right now. But as I come down, it's going to level out right at +2. It's never going to go past +2. It's never going to touch +2. It's going to get infinitely closer, but not actually touch it. So here, my y values are greater than +2. Okay, so there's my domain, there's my range. Your domain and range for all exponential functions should follow that same pattern. If you're talking about a real world situation, you're going to have a little more work to do. But if you're just looking at a graph, your domain should be all real numbers. Your range should be y is greater than whatever that boundary line is. If it graphs upside down, then it's less than whatever that boundary line is. Okay, constructed response. Yay. Okay, so let me pull out. So remember, this is the second time I've done this video because I screwed up my sound. So pulling out my page from earlier, so it's not as messy. Okay. I was about to say it is exponential growth. Compound interest. That's what I was trying to get at. Compound interest. My favorite thing to teach about. So, Kristen invests $10,000 in a bank. Okay, the bank pays 8% interest, and it's compounded monthly. So we have a formula, A equals P times 1 plus R over N to the NT power. I did not give you this formula. If you're in Miss Means' class, she may have given you this formula. I gave you the exponential growth formula. It's the same thing, it just looks differently. Remember, exponential growth is A times B to the X. Okay, this would be my A value. All of this is my B value. This is my X value. The other thing is, I taught you how to come up with the compounds on your own. I didn't, in this problem, you're given your compound numbers. I made you do it on your own because I'm mean. But, so maybe this is a little easier. All right, so we have A equals, A is the amount accrued, so that's how much money is in your account. P is the principal, which is your initial deposit. R is your interest rate. N is 12. And it tells you to put 12 in for N. Okay? And why are we using 12? Well, it's compounded monthly. So you divide your interest rate by 12, multiply your exponent by 12 to balance it. Okay, so in order to do it, so we're going to write our formula up here, and then we're going to do our math down here. So my formula is going to be A equals my principal, which is 10,000, times 1 plus R. Well, R is my interest rate, which is 8%. We're going to write that as a decimal, so 0.08. And that's going to be divided by 12. And we're going to do that to the 12t. Okay? If you go ahead and do the math for this and get 0.08 divided by 12 and add 1 to it. And I'm going to round. Now, remember, I think I talked about this in class. if you round and get something different from me because we rounded our numbers differently, that's okay. Now, should you be off by thousands of dollars? No. Could you be off by a few cents? Yes. And if you're off by a few cents, that's okay. That's just because we rounded differently. It should not be off by an insane amount, though. Okay, so when you do 0.8 divided by 12, you get 0.00666666. I rounded it to 67. So we added our 1 to it so that we don't have to take the interest, add it in, take the interest, add it in. That 1 adds it in for us. Okay, so, and then what I'm going to do is I'm just going to go ahead and put our formula down for all of these. And we're doing 12 times the year. So 12 times 1 is 12. 12 times 2 is 24. And we're just going to keep going. To the 36. To the 48. And to the 60. All right. And then when you multiply it out and you actually get your answers, we've got $10,830, $11,728.88, $12,702.37, $13,756.66, and $14,898.46. Okay, so you should have, so if you see it's accruing by $800 the first time around, or the first year, closer to $900 the second year, and then it's getting closer and closer to $1,000 each year till you get over $1,000. So that's the beautiful thing about compound interest, is that when you start investing and you start compounding, you get more and more money. It's so great. All right, so we have our data. We have how much we have at the end of each year. And so at year 0, when we invested $10,000. So that would be about here. So first thing you want to do is see how much each box is worth. So if 2 boxes is $1,500, what that means is that each box is $750. You're going to divide that by 2 to get there. Okay. So at 0, we're at 10,000. So that would be right in here. The first year is at 10,800. So that would be right in here. The second year was at 11,700. So that's right about here. 12,700. Right about here. $13,756. Okay, and at year 5, we're at $100 shy of $1,500. So this looks almost linear, but you can tell there is some curve to it. And if we were to zoom out and see more of it, you'd see some more curvature. Okay, so here's one of those where, do you connect the dots or do you leave it discrete? So my initial thought was, well, it's probably, gaining money over time, so it would be connected. But then if you think about it, you earn interest every time it compounds. So it's not compounded every day, it's compounded monthly. So you only earn money every month. So there should be a point. Now there should be like 12 dots in between here because it's compounded monthly. But it's still only compounded monthly, not constantly. So it's, so I think this one would be discrete because it's compounded monthly. I'm going to write that down. So now if you were to graph this on Desmos, you're graphing the function. The function will not graph discrete, it would graph continuously. And that's okay. I mean, it still gives you a good idea of, it would still give you a good idea of how much money you have in the bank. So it's discrete because it's compounded monthly, not continuously. If it was continuously compounded, then you would connect it. Like, this is one that you could probably argue either way. All right, 22, last problem. And one of my all-time favorite problems, because I don't like to teach geometry, but I do like solving geometry problems. It makes me feel smart. Okay, sorry, my throat's starting to hurt. Again, I did these videos twice, so I'm tired. And this was after a full day of teaching, so glad tomorrow's a quiz day so I don't have to talk as much. All right, so we want to find the area of the trapezoid. We have the area formula. So, just as a refresher, if you didn't know what a trapezoid was, a trapezoid is a quadrilateral where you have two sides that are parallel, those are the bases, and you have two slanted sides. The height of your trapezoid is from base to base. It's not a slant, it's a perpendicular from base to base. Okay, so if we have this area, we have the area equals half of base 1 plus base 2 times the height. So let's look at what we need. We need base 1. So base 1 is this segment here, which is 7y squared. Base 2 is this segment here, which is the same. If you look from here to here, this should be 7y squared. It's directly proportional with that. It's the same length. You also have 3 over here and 3 over here. So the whole base is 3 plus 7y squared plus 3. Well, 3 and 3 are like terms. You can add them and get 6. So base 2 is 7y squared plus 6. Okay, and then I need the height. So the height is not the slanted piece. A lot of people are going to plug the slanted piece in, but the height is actually this perpendicular distance, or this vertical distance. Okay, so I have, if you look, I have a right triangle here. I don't have the actual height. I do have the length of this side. I have the length of the slant. I just don't have this length. Man, I wish there was like a formula that would give me the missing side of a right triangle. Oh, darn. I wish there was something that would, oh, wait. Pythagorean theorem. Best friend right here. Okay, so this time, normally we have an A and a B and we're looking for C, right? This time we have a C value, so we're going to be looking for either A or B. Remember, C is your hypotenuse, which is 5. That's your long side, that's your slant. And then we also have this 3 that can go in for either A or B, it doesn't matter. Let's put in for B. So we have A squared plus 3 squared is equal to 5 squared. 3 squared is 9. 5 squared is 25. Let's subtract 9 from each side. A squared is equal to 16. Oh, and then that beautiful because you can take the square root now. Remember, to cancel out squared, you square root. A is going to be equal to 4. So my height, ooh, sorry. My height here is 4. Okay, I have all 3 of my variables. I can find my area now. So area is equal to half of base 1, which is 7y squared, plus base 2, which is 7y squared plus 6, times my height, which is 4. Okay, there's a couple of different things I can do. Easiest route I would go. So you could distribute this half, and then you could distribute this 4. Or you're multiplying 1/2 times something times 4. You're multiplying the 1/2 and the 4 already. So why don't we go ahead and do that now? So half times 4, or half of 4, is 2. So I've got 2 times 7y squared plus 7y squared plus 6. That's a little bit easier when I distribute. I could go ahead and distribute now, or I can combine like terms within the parentheses. That would make my life a little bit easier. So what's 7y squared plus 7y squared? Well, 7 plus 7 is 14, and your y squareds would stay the same. So now I have 2 times 14y squared plus 6. Okay, so I'm going to distribute my 2. 2 times 14 is 28. We leave the y squared. 2 times 6 is 12. And that's my area. Here, in units, that's area, so units squared. And that's it. This is the hardest part of this problem, is Pythagorean theorem to get your height. If you can handle this part and get your height, the rest of it's plug in and simplify, and you should be okay. All right, so this is the end of the Unit 4A practice test. I know it's lengthy, but I hope I gave you some good explanations. I hope that you understand the constructed response. I hope you understand the problems from the practice test. So thank you for your attention. I hope you guys have a great evening and a great day, and I will see you guys soon. Bye.